Well, good afternoon. I'm Rich Blomseth with Echelon Corporation. I'm a product management director there, and I'm going to talk today about the industrial Internet of Things and how it applies to smart buildings and what I think we can do for smart buildings in the future. So I'll talk a little bit about the market disruption that the Internet of Things is causing, and more specifically talk about the industrial Internet of Things. Then I'll talk about what Echelon is doing because of that disruption, some of the changes we're making, the new platform we're introducing, and then give you a little bit of a conclusion. So first of all, who are we? Who's Echelon? So we're a worldwide corporation headquartered in close by in San Jose, but with offices in the countries listed here. A couple hundred employees, close to 100 million in revenue, and about 250 million that was spent so far in R&D creating the platform that I'll talk about. We're very patent-rich with over 65 patents in the technologies that I'll be describing. We started in 1988. We're actually started by Mike Markkula, who was one of the founders of Apple. And he had the idea of creating very low-cost computers that could communicate with each other. And that's really what the basis of the company that he started in '88. I started there in 1989, so I've been there since close to the beginning. We went public in '98. Our initial platform is always designed to be a very horizontal platform, a general purpose automation platform for creating smart devices that communicate in a variety of applications, whether those applications are in buildings or in factories or in trains or even on subways. So it's a horizontal platform, and we are used in many industries, have been used in many industries. But buildings has become a very important part of our business. And we have been in commercial buildings for some time, and all the major commercial buildings, control systems manufacturers like Siemens and Honeywell and Johnson Controls all use our technology to implement some of their products. Around 2000, we also got into the smart grid, so we also make energy meters. Nearly every energy meter in the country of Italy actually uses our technology. Unlike buildings that communicate over twisted pair of wires, our meters communicate using power line technology, communicating from the meter over the power line, providing the power back to data concentrators that in turn provide data back to the utilities. Lately, we've also been getting much more into outdoor lighting, so smart lights that can be controlled even based on motion, based on time of day, based on outdoor lights. That's become a very rapidly growing market, especially in Asia. So we're still in all these various markets and have products in all these markets. We've shipped over 130 million transceivers, so there's quite a few of our transceivers out there. But the market disruption we see going forward is the industrial Internet of Things that I'll talk about. So we hear a lot about the Internet of Things and it being the next big wave in computing. We see a lot of projections from a lot of analysts as to how big it's going to be. But the key thing is it's part of the same growth we've seen over the years, where when there was mainframes, there was sort of millions of computers, and then as we got into work groups and networks of computers, we had hundreds of millions of computers. As the computing market has grown to be more corporate and more consumer-oriented, we've got into billions of computers. But as we get into computers going to all kinds of devices, all kinds of everyday devices, the market's going to grow into tens of billions of computers. And that really was part of Markkula's vision when he started in '88. He said, this growth is going to keep happening, because each of these steps occurs because the cost of computing comes down. And as we also enable communication between computers, the value of the computers goes up. And what will happen is, as we have the Internet of Things, that's going to converge applications that used to be very separate. And if you look at what happened with the Internet and the World Wide Web, before the Internet and before the World Wide Web, there were a lot of computers, but for the most part, they were separate. They didn't really talk to each other. They were like little silos of information. The Internet allowed those to start communicating with each other, and allowed those to create more value as you could have communication between computers. The same thing's going to happen with the Internet of Things. Today there are lots of automated devices out there, but they're often standalone systems. There might be, for example, in a building, you might have a standalone lighting system, a standalone HVAC system, a standalone security system. So each of those is a little silo of control. And what the Internet of Things will do is bring this IP connectivity into all these markets where the Internet of Things applies and allow these silos to come together. So let's look at an example of a converged smart building. So by having a common community devices platform, we can now have HVAC, lighting, security, elevator controls, all on a common platform. So as an example, we have an employee that arrives in a building. The employee swipes his badge and he comes into the building. The office temperature gets adjusted because now we know the employee's going to want a comfortable office by the time he gets to his office. The lights can turn on because they know that the employee needs a certain set of lights. You can activate the elevator so the elevator's at the right position. The elevator comes to the employee and everything is ready to go. So each one of these little steps was something that was possible today, but it's the linkage between them is the new piece that the Internet of Things really brings for us. Now the Internet of Things itself is a very large segment, right? It's really any kind of smart device that communicates with other smart devices other than the ones you traditionally think of. So it doesn't include PCs, it doesn't include mobile phones, it doesn't include tablets. But it does include all those other things that communicate. That's the Internet of Things. And the projection, one of the projections of how many of those other things there will be is 50 billion by 2025. And this projection, this is from one of the analysts, kind of broke down those things into different markets, saying, well, where are all those things? And there's some percentage of those things that are going into what they call industrial application. And industrial really means anything that's not consumer. So it includes smart buildings, includes transportation, includes traditional industrial, like factory automation. And they also broke it down into consumer. And if you look at the 2014 line, well, it's not 2014, but the 2013 line there, you'll see, today the largest segment of the Internet of Things is consumer automation. Right? So things like Fitbits and Nike Fuel Bands, those are Internet of Things devices that are Internet-connected devices, but they're for consumers. But the interesting segment for us is that industrial segment, the darker blue segment, which today is a smaller segment of the Internet of Things, but it's forecasted to be the largest growing. And you see by 2020, somewhere after 2020, the industrial Internet of Things becomes the biggest segment of the Internet of Things. And that's really our market. Things like smart buildings, smart factories, that's going to be where the real growth will be. So we look at the structure of a typical industrial Internet of Things application. We believe that many of these applications will be built around communities of devices. If you think about a smart building, there's really a community of devices within the building, and by community we mean devices that communicate with each other. Like my example, that badge sensor that's talking to the HVAC system to get the temperature right, that's talking to the lighting system to get the lighting right, that's talking to the elevator to get the elevator to the right position. That's communication within the community. And that's communication that doesn't need to happen between the community and some server sitting in the cloud. It can all be right within the community. Right? So when the person comes in and badges in, we don't have to have the cloud tell the elevator to come down. We just want it to tell the elevator directly. So we see these various rings of data, where at the bottom we see sort of the small data. And at the top is the big data sitting up in the cloud. But we like to say, that there is no big data without the small data. Right? The small data is all those sensors out there, the temperature sensors, the pressure sensors, the flow sensors, the badge swipe readers. That's the small sensors creating the small data. But all that data aggregates, all the data communicates, creates the community, and all the data also flows up into the cloud so you can do analytics and diagnostics of that data over time. So we see these different layers then. So cloud analysis at the top, ubiquitous access to all these different kinds of data, but then the very important device layer at the bottom, which are all these communicating devices and autonomous devices, which means they can run by themselves and communicate by themselves without the need for a separate server or separate gateway. So why now? Why is the industrial Internet of Things happening now? And we see three reasons. One is hyper-competition. Internet of Things has become a very hot topic. There are a lot of companies getting into it because everyone sees this incredible growth. Everyone sees that growth as an opportunity to create new markets, and so there's a lot of competition. But that ends up being a good thing for the people buying the technology because you have more choices. And the capability of connecting everything to everything that IP brings and that the Internet of Things brings is fairly new, and something that's very important in driving the market. And the incredible growth in server capacity so that you have nearly infinite capability of analyzing data produced by all these things at the edge. So that's what we see as the market disruption. So what are we at Echelon doing about that disruption? Well, we're introducing a new platform. We call it the IZOP platform. The name comes from Industrial Internet of Things. There's two I's in IIoT, so that's the IZOT here. And what we are doing is introducing really the world's first multimedia, multi-protocol platform for the Industrial Internet of Things. So we see this rapid growth, we see this rapid opportunity. And in 2009, there was roughly 900 million devices in this sort of market. And we had a good share of that, about 100 million of those devices. We see that opportunity growing a lot by 2020, which is that sort of industrial segment of the Internet of Things. And we think we have a platform that can address a large part of that growing market. And what's unique about it is that it works on both wired and wireless media. So it's much more multi-link than some other solutions out there, and it's also multi-application protocol. We can run our existing LONTalk protocol, which is used widely in buildings. We can run the BACnet protocol because it's an IP-based system. BACnet IP runs on top of it just fine. BACnet's used widely in buildings, so we support both. So it's both LongWorks, BACnet, all on top of common IP links. So how do we do that? So we're creating a platform that allows you to create community of devices, allows you to add routers to connect those communities into the cloud, and also includes cloud solutions. So what is Echelon providing? So what we're providing, first of all, are chips, so that manufacturers can create the smart devices within those communities of devices. We're creating software stacks that can be ported to any processor. So you don't have to use Echelon chips. You can just take our software stack, port it to an ARM processor, and run that ARM processor as a smart connected device. And we're also providing modules. And the modules are more for wireless connectivity, so we're working on Wi-Fi modules, we're working on 802.15.4 modules. And the advantage of having modules for wireless connectivity is that getting wireless devices certified is usually a very expensive process. By having modules, we can do the certification for the manufacturer to decrease their cost of developing a wireless device. So we're creating all three, chips, software, in some cases free software, and modules for creating those devices that form the communities of devices. We're then also creating routers that then connect those communities to the cloud. So the router is not required. If all you want is a set of devices communicating over a twisted pair of wires, then all you need are the devices themselves. They're autonomous, they can talk with each other, they can create a system by themselves. But then if you want to take that system and provide remote access from the cloud, or take that system and push data into the cloud, that's where you add the router. And so we'll also have routers for doing that. And then finally, the cloud is where we'll be introducing software for managing those networks, for monitoring those networks, for remotely controlling those networks. So the cloud gives us a nice remote capability, but the cloud's not required. So the advantage is that we can now create a single architecture that works across multiple media, that supports multiple application protocols like LONTalk and BACnet. It allows manufacturers to actually create fewer SKUs, because now you can have a single device that acts both as a LONTalk, LongWorks device as well as a BACnet device, and provides manufacturers with very fast time to market with off-the-shelf chips, off-the-shelf modules, complete software stacks, all ready to go. The one thing we have in common between all these various solutions, so I've said we're multi-link, wired, wireless, we're multi-protocol. What we have in common across all these links is a common set of control services. We call that the IZOT control services. And whether a device is using one of our chips or just using our free software or using one of our modules, the control services stay the same, and that's really what was added on top of traditional IP. So the control services allow devices to communicate with data points. So a temperature sensor can publish a temperature, a pressure sensor can read a pressure and publish it. Something that controls something, say a lighting controller, can have an input data point that says here's the state of the lights, or here's the color of the lights, here's the level of the lights. So it's a very simple publish-subscribe model. So in the beginning we had the card swipe sensor. The card swipe sensor has a data point output of whatever the card swipe was. The controller that needs to make a decision based on that employee come in has a data point input where it subscribes that information. So we allow connections or bindings between devices so that devices can communicate directly with each other, exchange data with each other. And each of these data points can be up to 228 bytes. So we can transfer large chunks of data then between devices to set up a control system. The other thing we add on top of IP is simple unicast and multicast addressing. So you can have a community of devices with up to 32,000 devices. And we do have buildings today with, say, 18,000 devices. There's one in Paris that has 18,000 devices. So these devices can all communicate with each other. They can form groups of devices within that network, so up to 256 groups. And we have different protocol services. So we can either have simple unacknowledged messaging, where you just send a message and don't wait for a response. You can have acknowledged messaging, where you send a message and wait for a response, and the response doesn't come back. You send it again. And that even works with the multicast case. So say I'm sending a message to 3 devices, I wait for the 3 responses. If I get 2 responses back, I send the message again to that 3rd device. Another very strong feature of the Long Talk protocol has been the number of profiles that we have. The profiles kind of define the interface to the device from the network perspective. So for example, there's a VAV profile for how the VAV appears in the network. And there's hundreds of these profiles, hundreds of these types. And we keep the same profiles and the same types with the new IZOP protocols as well. And we have capabilities of doing self-installation where devices can actually install themselves. They can discover other devices in the network and automatically set up connections between devices. Or for larger networks, we also have management tools that can allow the devices, well, for an integrator to specify how the devices communicate, how they get installed. I mentioned one of the things that we're providing are new software stacks. So the software stacks are basically the implementation of this protocol that I've described. We have a large stack called the Device Stack EX. That's a free download available today from iiot.echelon.com. It allows developers to create applications in Python, C++, or C that implements this protocol. We include full source code for the stack. There's no royalties required. So you just port the stack to your processor and you've got all this capability. The EX, like I said, is the big stack. It's about 1 megabyte of code. We've done ports of the stack to Raspberry Pis and BeagleBone Blacks, which provides a nice fast way to get started with the stack. Raspberry Pi is a $35 Linux computer. BeagleBone Black's a $45 Linux computer with twice the performance of the Pi. So you can start with those processors if you want. Just buy a $35 Raspberry Pi and run the stack. And again, it's all free. Or once you have it running and you like it, you can port it to whatever processor you like. We also provide code and example schematics for an example lighting system so you can see how to implement devices using this stack. We also are working on a smaller stack called the DX stack. It's for more memory-constrained devices, such as the smaller ARM processors, the M-series processors. We're doing a first port of that stack to a Marvell 88MC200, which is a small ARM processor from Marvell with a Wi-Fi chipset. And both stacks support patented self-installation, which I described earlier, which is the self-discovery of peer devices and creating connections between devices. We also have a server stack that's also available for free today. And so the free edition that you can download today will have a premium edition that adds some additional capabilities like routing and multiple links and includes support. The free versions aren't supported. The server stack implements a REST API that makes it very simple to create web pages. So web pages that interact with the network, that monitor the network, and then control the network. And the IZOP router that I mentioned earlier actually has the server as part of the router. The server stacks also include for full source code, so they can be ported to other processors as well. And the REST API makes it very easy to interact with the stack from a web page. A simple command like get API devices will give you a list of all the devices in the network and their types and their status. And a simple command like shown at the bottom there will give you all the data points in the network that are reporting temperature. The stacks include a sample application for the Raspberry Pi for the EX stack. And we actually have the example running here while we're bringing it up. We're having some Pi problems right now, not stack problems. But the example shows you sort of an example lighting system. How can you actually control lights using Raspberry Pis? So we use one Pi as a keypad where you can select buttons on the keypad, another Pi to control color LEDs, another Pi to read sensors that report temperature, humidity, light level, and occupancy. And again, all that source code is included with the stacks. And then the server stack can run on another Pi or on a BeagleBone Black. We prefer the BeagleBone Black for the server because of the additional power. And then we include sample web pages. And you see the picture of the sample web pages here that can monitor the lights, monitor the energy usage of the lights. The one in the middle actually allows you to put, point at a color and set the selected lights to the selected color. And the bottom page is a charting page. It allows you to sort of chart data. So if you want to see, for example, the light level over time or the power usage over time, you can do that from the charting page. And again, all the web pages are included with the stacks as well. They're just standard HTML5 and JavaScript, so you can start with those, make your own. So that's the stacks. Now we also have system on chips options. So you don't have to use our chips, but if you want to use our chips, it allows you to create lower cost devices that communicate over twisted pair media, very low cost twisted pair media. And so today the most popular media that we sell for commercial buildings is free topology twisted pair, which is just a simple pair of wires that can be wired in any way you want. It could be a bus, it could be a ring, it could be a star, it could be a combination of the above. So it makes it very easy to install. It's only 2 wires versus Ethernet, which is 8 wires. And the 2 wires are polarity insensitive, so if the installer hooks them up backwards, it doesn't matter. It just works. So very simple to install. We're working on a faster version of it called Megabit FT. That would be sort of the next generation of free topology. That will be closer to megabit in performance. So sort of a lower cost alternative to both Ethernet and RS-485. And we also have powerline media and next generation powerline media. So I mentioned free topology and how it gives you a lot of flexibility in how you can install a network, and it's very popular in smart buildings today. You see an example on the right of what free topology means, right? You really can have very sort of random looking wiring between the devices, and it just works, right? So the technology handles the reflections and problems that you have as you wire things in odd ways. So it really gives you a much lower cost media to install in Ethernet and a much simpler media to install than RS-485. And one thing about the new chips that I mentioned, the new chips support both LongWorks and BACnet on the same chip. So it's actually possible now to create devices that have both a LongWorks interface and a BACnet interface with a single SKU, a single processor, and actually to support both LongWorks and BACnet at the same time. And we actually showed this at AHR Expo earlier this year. So we had a demonstration of some beta products from some of our customers where they had building controllers that were implementing both long-talk IP as well as BACnet IP within the controller, talking through a router, and we had 2 workstations sitting in the network, one running a BACnet workstation, the other one running one of our OpenLNS workstations. And the 2 workstations were working simultaneously, and as you change something in the controller, you would see the feedback at the same time in both the BACnet side and the LongWorks side. I mentioned the Wi-Fi modules. We're working with Marvell on those. And Marvell has a nice software development kit for their modules. They call the EC Connect SDK. And so we're adding a software module to the SDK to allow you to create software for this new Wi-Fi module. So we're porting our DX stack to their module, and then actually we'll create the module as an Echelon product that already has a stack in it, is already certified, and is ready to be embedded into a product. So why might you want to work with us? Well, we do have a very proven solution. As I I said, deployed over 100 million devices. Their reliability has been proven to be very high. We're taking that same technology that we've been deploying for the past 24 years, bringing it to the IP world, bringing it to the Internet of Things world, and providing the same level of reliability for these kinds of solutions. We've proven we have a solution that has industrial scale. We've proven it works in networks with 15,000 plus devices, but you can also create small networks with it. We go into very challenging environments like outdoor street lighting applications, and works very well. And we have a certification body for certifying these applications. And it's a very unique multi-protocol, multi-link, multimedia platform that allows coexistence of both long-range devices and backnet devices within a building. So giving very low risk migration to the IP and to the industrial Internet of Things. So in conclusion, we think the transition to the industrial Internet of Things is really a very materially significant opportunity. Projections all say it's very big. We believe it's going to be very big. We think we're in a very unique position because we do have 25 years of experience in creating control networking products. And we believe we have a solution that allows you to create products that are either LongWorks only or a combination of LongWorks and backnet, or just use some of the new technologies. And we have a unique solution that allows you to create both wired and wireless solutions, or any combination of those, and a solution that allows you to create either solutions for the premises or that combine on-premises devices with a cloud solution. So we've started the IZOC product rollout. It's a fairly new platform for us. It was just introduced a few months ago, but it's starting to come out. And our new single chip solution, FP6000, that supports both LongWorks and backnet, is a real game changer that's very unique within the market. And we think the time to start working on this is now. So thank you. And